Okay, so very good, very good. So let's get started. Today, today we are going to talk about the finite element now. We will start from the beginning, from the very fundamental introduction about the finite element, and then the very fundamental direct method. Okay, using this direct method, we can analyze a series of different elements, such as the spring elements, bar elements, and truss elements. So it's a very fundamental method, very fundamental concepts important in the finite element analysis. Okay, so to pay attention to pay attention to the fundamentals, and let's go through them together. Okay, so some of you have asked me about the questions in the mathematical review. That's great questions. And I think we have provided the examples and we have uploaded the slides in the Canvas now. You can go through them and then watch previous video we recorded. Then you should be all fine. Okay, very good. So now let's get to the finite element analysis. Yeah, can you guys hear me? Can you see my shared screen?
Yes.
Yeah, excellent. Let me change it to the point. Okay. Yeah, this point. Okay. Good. Yeah, here are the faculty members and the staff members who are helping us, supporting us for this class. We really appreciate their support. And this is me. And by the way, I just want to remind you that 5 times policy that Professor Mark Shaplick recommended. Okay, so when we started to talk about those fundamental things, and then we gradually step into more sophisticated finite element analysis, make sure you follow this 5 times policy and then review the material frequently and then understand the material better. Okay, I hope you all get better and better in this very important field, very important subject. Okay. And also, many of you have sent me a very positive survey after the class. That's excellent. That's excellent. And I have answered the questions you have individually. And if you have more questions after each class, please feel free to send the survey to me. That would be great to improve our class together. Okay, very good. Yeah. Now, in terms of flowchart, right now we are in this region. We're in this region now. Okay. And just a reminder, we have 3 videos in the Canvas. Make sure you make a copy of them. After we finish these 3 videos, I will upload 2 more videos about the abacus, and then 4 more videos about the lecture we have pre-recorded for the advanced materials. Okay, so make sure keep a copy of them video as well as the PowerPoint slides. Yeah. Okay, let's get started to the point. So overall, before we touch any engineering, any concepts of finite element, if we just think about the overall engineering analysis, talk about any if we want to analyze any engineering problem, in fact, we will take mainly 4 steps to analyze them. Can you guys hear me? Okay, very good. Let me turn off my video in case just to save some bandwidth. If bandwidth is fine, if we find it's fine, now I can turn on the video again. Okay, I hope you can hear my audio without any interruption. So good. Okay, very good. So in terms of the engineering, in terms of to analyze any engineering problem, we can basically use 4 steps to analyze the problem and solve the problem. Okay? First step is to idealize the system. Means we can simplify the system, make the system to be more simplified in a reduced manner. Means we capture the essential part of the system and then look at those essential parts. For the trivial part, we put it aside for now. Okay, so that that means idealize the system. Second step is we look into the system, find out the equations, find out the physics equations or mechanics equations involved into the system, especially equilibrium equations, right? In the physics, you have the energy equilibrium. In the mechanics, you can have a force equilibrium, momentum equilibrium, right? Both linear momentum, angular momentum, they will be in the equilibrium, right? So for the static problem, right? So we need to find out all those equations, list those equations, along with the boundary conditions, compatibility equations, right? List all those equations that can be used to describe this idealized system, and then put them formalize them in the correct way. Okay. Then we solve the equation. We use the different method to solve the equation, either mathematical way to solve the equation, or sometimes use the computational ways to solve the equation. Use the mathematical way, you can get the analytical solution. You have a final conclusion expressed in a new equation, right? But using a computer, you can get a numerical solution. You can directly get the solution, get a number, right? After that, we will need to interpret the results, whether those results are reasonable or not, whether they make sense or not, whether those results can be extrapolated into a bigger field and then form some general principles or not, right? So those are the interpretation of the results. If the results is correct, then this engineering system is solved, and then we can gain new understanding now. If the results cannot be interpreted, results is very weird, then we need to go back to the beginning, start from the step 1 on again. So we need to re-idealize the system. Maybe what we find, those essential parts are not sufficient. There may be some trivial part we removed. They actually are important. They are critical. Then we add new things in to re-idealize the system, and then rewrite, reformulate the equations, and then solve them again, and then see the results. Okay, so interpret the results, and then we repeat this procedure in an iterative way until we find the final results are reasonable. Okay, so those are the 4 important steps that we need to perform to analyze the engineering and physics systems. When in this class, when we study finite element method, we actually will use the same format for these 4 steps. Firstly, we idealize engineering system. Either they are the beam system or truss system or other 2D or 3D different structural system. And then we formulate the equations. And then we solve the equations using the mathematical method. We already discussed the matrix operation, solve the eigenvalues, and then find the maximal, minimal values that we described in the last lectures. Okay, and then we interpret the results. Okay, so that's the overall overarching 4 steps we will use to solve engineering problem. So, do you guys hear me?
Yes.
Excellent, excellent. Now, I want you guys to learn more things. Okay, so what I'm saying here are only engineering problem. This engineering problem, they are dealing with the material that is non-living material. Okay, right now the science has been broadened to involve many new materials, including some biomaterials. If you have biomaterial, these 4 steps roughly still applies, but they need to be enriched, because biomaterial in this system, they are not only equilibrium, they contain many non-equilibrium process there. Okay, many non-equilibrium process or far away from equilibrium. Okay, then this process you can still use these 4 steps, but you need to make sure every step is done correctly with correct bio information incorporated. Okay, I just want to give you one very quick example. What is a biomaterial? So here, so here, what you see on the left-hand side is a tumor, is a human tumor. Okay, so you in the center. Do you guys see my shared slides and my PowerPoint? My dot.
Yes.
Yeah. Okay. Very good. So on the left-hand side, this is a tumor, human tumor, solid tumor. Those lines, those red channel lines, they are vasculature. Okay. So those vasculature are connected with tumor, support the tumor with the nutrients to let them grow. This is the human body. Okay, human body have different cells. You have a neuron, you have brain, they consist of a neuron. You have muscle, they consist of muscle cells. You have the bone, bones consist of osteoblast, osteoclast, and many regenerative stem cells in the bone. Okay, now if you are engineer, you look at this problem. Look at all this picture I showed here. If you are engineer, mechanical engineer, one feature you will quickly realize is all those different material, they have different mechanical material properties. For the brain, they are actually very soft. They are like 1 kilopascal, 1,000 Pascal. Pascal is a Newton per meter square, right? 1 kilopascal is like this Young's modulus. You know the concept of Young's modulus, right? You learned from the mechanics of material. Young's modulus is the quantity that people, is the unit people use to describe the mechanical properties of the material. So the brain is 1 kilopascal. This Young's modulus is like that of tofu, of the cheese. Okay, very soft. And then muscle is a little bit stiffer, 10 times stiffer, right? 10 kilopascal. Bone, this is a rigid bone. Actually, this bone is pre-calcified. It's not that rigid. Okay, you have even more stiffer bones. But here, this bone, pre-calcified bone, is about 30 kilopascal. They are all, you can quickly see different part of the body. They have different Young's modulus. And then look back at this tumor. They are actually very stiff. They are like this precalcified bone, have 20 to 30 kilopascal. Okay, for the tumor. So as a mechanical engineering, when you look at those things, if you look at, you think they are non-living material, you will soon find out that they have different mechanical properties, mechanical material properties. You will soon find out this. But this is an engineering point of view. Is there, so Thomas asked a question, is that yield stress? It's not yield stress. Your stress is also described in the same unit, Pascal. But stress and the Young's modulus are different things. The stress over strain in the elastic region, if you divide the stress over strain, then you will get the Young's modulus. But when the strain go even higher, past the elastic region, go to the plastic region, the material get a yield. That is stress value is yield stress. Okay, so here we are talking about different things. It's a very good question. Different material, they have different Young's modulus. They also have different yield stress. Yeah, I'm not showing yield stress here because they are less relevant than the Young's modulus here. Okay, very good question, Thomas. Can you hear me, Thomas? Yeah, okay, I saw your message. Very good. Can everybody hear me? Yeah, excellent, excellent. Now, if you look at those material from a biological perspective, these cells here, those cells showing here, they actually are not just statically stay there, maintain their Young's modulus. They actually will interact with this environment. And then when they interact with environment, this brain cell, neuron, they will know environment is very soft. Okay, the muscle cell will know environment is very soft, intermediate soft. Okay, they know it. And in case those environment change, they become stiffer. If in the brain there is a tumor growing, and then local region of the brain will become 20 to 30 kilopascal, then there is a stiffness landscape there. Some part is 1 kilopascal, healthy brain. Some part is stiffer. The brain has tumor there. 20, 30 kilopascal. Those brain cell, those neuron will sense it, and then itself will change their property. Okay. Then in that case, this system, idealized system, changes. You need to consider that so that you can write correct equilibrium equations. Okay. So previously we have discovered that in the human you have cancer cell. You have the colon cancer cells. If you culture those colon cancer cells on the environment that is similar, that has the mechanical stiffness similar to those tumor stiffness, cancer cells cultured on those environment, they will become very invasive. They will start to migrate. They will start to invade the tissue. Okay, so you see here those single rounded cells. Those are invasive cells, very invasive. You see here the bunch of those connected many cells here. They are not invasive, but they are experiencing the environment, and then they become invasive. They gradually detach from each other, become invasive, and then in the human body, those cells will start to invade the body, and then generate secondary tumor. That's a very big issue in the cancer. Okay, so that will completely change the system, Okay, and this system will react to it. Human also has immune response, right? So they are fighting with each other. Then they will form new equilibrium. Okay, so what I'm showing you here is I want to let you know, in our class we don't need to consider those complicated case for now. You firstly focus on understand how to use finite element to analyze static, structure, mechanical system. No biological system involved for now. Once you understand everything here, then if we have time, I can show you some system that adding biochemical factor, biological factors in to change the system. Okay, so I just want you to know that these 4 steps are important. You firstly master them, and then gradually you can start to tackle more complicated questions, such as those bio-relevant questions. Okay, so let's get back to the fundamental things first. So here is the flow chart for that 4 steps. Firstly, we studied the physical problems, and then we establish finite element models of physical problem. Using this model, we actually can write different equilibrium equations in the system, and then we solve the model. Model means that the idealized that system, right? We solve the model, and then we interpret the results, and then we can go back. If the results is not reasonable, we revise the model, refine the model. Okay, so basically follow this process to solve any finite element problems. Okay, so now let's get back to the very fundamental things, and we can start the direct method. So what is direct method? So let's start from a 1D system first. So here is a 1D system, consists of springs and some objects and walls. So you can see here, this one has 2 walls. This one wall, this one is wall. Can you see my laser point? Yeah, okay, good. I saw a question here. Let me see. Question from Sarah. Is the process a loop from the previous slides? Excellent question, Sarah. Excellent. Yes, that is a loop. The process is a loop. It goes, let me go back. Very good question. Very good. This is you start from idealization of the problem, and then you start to solve them using the 4 steps process we mentioned. If the final result is not reasonable, you loop it back to redefine the system, redefine the model, and then start over again until you finally get a reasonable results. Okay, so that's a loop, iterative method. Okay, it will not, and also Sarah asked, does it stop at any point? It will not stop. It will stop only at this point, at the final interpretation of the results point. Okay, very good, Sarah. in the future, you don't need to send a message in a direct manner in the chat. Just send it to everybody so that people can see your question. Because your question may also be also are the question of your classmates. So you ask those questions, that's excellent. Everybody can learn from the discussion of these questions. Okay, just send it to everybody. Yeah. Sarah, can you hear me? Yeah, excellent, good. Okay, direct method. So for the here we show 1D system of the springs. We have the walls here. Walls means these two are infinitely rigid. You cannot move it. You cannot move them. So they have so you will have zero displacement on the wall. Here, on any point here, will not move. Zero displacement, no displacement, no translation. Okay, no translocation at all. Okay. However, they can have force. When you apply force here, force is there. Okay, but there's just no displacement. Okay. This one is called spring. This is called spring. So this dashed waveform, this is called spring. Okay, different springs. With different springs. This spring can deform. It can also sustain force. Both force and displacement and the deformation can happen on the spring. This green part, this shallow green blocks, we call it just a block. We just call it block. They are the point that connect different springs together. For example, this is called number 2, right? This number 2 block connect spring number 1 on the left hand side, spring number 2, number 3 on the right hand side. Okay, so this is called block. Actually, we also call it a node, N-O-D-E, node. Okay, that's more conventional way. Spring we call it element because the spring can get deformed. Okay, they call it element. This node actually cannot be deformed. They can only move. But they cannot be deformed. Okay, so here you can see we have 2 walls, number 1 and number 5. They all circled with they all enclosed by the circle. We have 3 nodes, number 2, number 3, number 4. They are enclosed by a circle as well, right? The number. And then those walls and nodes are connected by the springs. The spring number 1, 2, 3, 4, 5, and 6. And also there are external force applied on those nodes. Force number 2 applied on the node number 2. Force number 3 applied to the node number 3. Force number 4 applied to the node number 4, right? So this system contains external force applied to the internal combination of spring and node. And overall, this combination is connected with the wall on both sides. Okay, so in this case, you can imagine when the force, you see 3 force applied all towards the right hand side, right? That means the spring on the right hand side are mostly like compressed. Spring on the left hand side are mostly get stretched, right? And the wall are sustaining the force, making everything into an equilibrium state, right? So they are force equilibrium. And in the system, some of the spring on the tension, some of the spring on the compression, right? So this is a common view now. Do you guys follow me? Yes. Okay. Time. Okay. Good. So when you think about that, then when you think about this is a internally stressed system. Okay. What we are going to do is to find out under those external force and within this kind of organization, what's the force and displacement in each spring? What's the force there? Okay, so then if once we know that, we completely understand this system in this condition, right? We know the mechanical, we can know the mechanical status of this system. This is called a 1D system of springs. Okay, for this 1D system. Now, in this 1D system, there are several things we need to know. Firstly, because it's 1D, So all the bodies, including nodes and elements, only move in the horizontal direction. They cannot move vertically, only horizontal direction. External force F2, F3, F4 are applied, and they are also in horizontal direction. Okay. And in this case, in fact, we already separate the nodes with the springs. Then we actually already in a discrete manner. If you have a large body, continued body, they have a 3-point force applied, and then 2 displacement boundary conditions applied on each side. Then to solve the stress status inside, you need to discretize that continuous body into many, many small elements. That is making the whole continuous body into small finite elements. But here we don't need to do that because it's already separated into single springs already. So each spring, we view them as an element. Each connecting point, we call it nodes, and the wall is also the connecting points. Okay, so now you know that the convention to denote the node is actually use the alphabet, use the number, digital number enclosed by the circle. That is nodes. For the elements, we use just the number, Okay. Good. So now in this case, to solve the force there, we need to use the force equilibrium condition. Each spring is in a force equilibrium. Each node is in a force equilibrium. Okay, and then by listing their equilibrium equation, we will have a set of equations, and then we solve the equation one by one, and then find out the unknowns there, which is the force and displacement there. Okay, that's our step. But to do that, we should follow a very systematic way. There's a very systematic way we can follow so that avoid any possible mistake. Okay, so to do that, to be systematic, we need to write the connectivity table, okay, which is this table. So we write the node, we write the node that connected with the spring, and then we write the spring which has their corresponding node together. Okay, so this is the overall picture, right? The same picture as before. Now we write them together the numbers together into the connectivity table. The way to write is we write from the left-hand side to the right-hand side. We first identify element number, and then we find out their corresponding node connected to the both ends, from left to right. So for example, for element number 1, we have this one, number 1. We have node number 1 connected with it. That is connected to the wall on the left-hand side. On the right-hand side, we have node number 2, right? Node number 2 that is connected to this object, right? And then spring number 2. So a second row, spring number 2, which is also called element 2. Number 2, it has node number 2. Okay, it has node number 2. And then on the left-hand side, and then node number 4 on the right-hand side, right? Element number 3, you can see here, number 3 here, it is connected to node number 2 on the left, node number 3 on the right. So here, 2 and 3, which is this one, 2 and 3. And then element number 4 is a spring number 4, this one. It has a left-hand side node 1, right-hand side node 3. So 4, 1, 3. Element number 5 has node number 3, node number 4. So 5, 3, 4. Element 6 has node number 4, node number 5. So 6, 4, 5. We follow this convention. Or write the element number first, because element is most important. You want to find out the force. You want to find the information from the element. Okay, and then write the node from left and the right in two separate columns. Each element is connected to only two nodes on the left and the right. There won't be three nodes. Okay? And then following the sequence from left to right, we avoid any confusion. Okay. Now, once we put all these things together to form this connectivity table, we will find we altogether have six elements, right? We altogether have 5 nodes. Okay. So this is the most important first step when you use direct method to analyze 1D system of springs. This is the most important part. Many students made a mistake in this part. If you follow what I just described earlier to write this table carefully, then you can solve almost all the problems. Okay. So in this case, due to this arrangement of the node and element, we have this table. In the exam or homework, we can change this. We can change different assembly of the spring and the object. Then you will have different tables, but the principle to make those tables are all the same. Okay, can you guys hear me? Yeah, excellent. So make sure that you practice by yourself. Okay, practice by yourself to construct this table. Now, after this table is done, let's look at the elements individually, and then we can start to write the equilibrium equation for each element individually. Okay, so let's look at the single element, those are spring element. So here you see, this is a spring. This is a spring. Okay, this is a spring. We call it E, spring E. Okay, this is just a notation. We call it E. E spring. It has 2 nodes, right? It has 2 nodes. We call them, to be generalizable, we call it I and J. It can be, if you go back to here, that E, if for the element 1, E equal to 1, I equal to 1, J equal to 2, right? From left to right. For the element 2, E equal to 2, I equal to 2, J equal to 4, right? Same thing. So here we just to be generalizable, E, I, J, use this to denote this spring. Now, and also you see the node number actually is enclosed by the circle, right? So that's our convention. Now, this element E consists of a node I and J. It also has a spring constant. Every spring has a spring constant because when you apply force to it, the spring will deform. The deformation of the spring and the force applied actually hold in a linear proportional relationship. Larger force, larger deformation. Smaller force, small deformation. But they are ratio. The ratio, you divide the force by the deformation, you get a ratio. That ratio is constant. That the constant is called a spring constant, K. This K, we write it K with the bracket parentheses E, right? So that means that this is a spring constant of spring E. Do you guys follow me? Do you guys hear me? Yeah. Let me know if you think I speak too faster or I speak too slow. Let me know. I can adjust it. Okay. Right now I'm using the same pace. Last time you feel comfortable, but now material is different. Okay. We get more and more into the important material now. If you want me to slow down or you want me to speed up, let me know. I can do that for sure. Okay. Okay. So the spring constant of this spring is K with parentheses E. Okay. Now, in the system, this spring is subjected to the force. The force is applied. So we can denote the force there. In the node I, we can assume force is towards right, from left to the right. Okay. And then this point is under force. This force we call it Fi. We put the node number as the subscript. We put the spring number, spring E, spring number with the parentheses at the superscript. Okay. So this one is the convention denotation. Once you see this, you will know, oh, this is a force. And also force is small. It's not a capital force, right? Small force means internal force. It's internal, not external applied. External applied usually is big capital force, like here, capital F. Okay. So this one, FIE, means the internal force applied to the node I of element E. So that's the meaning. Okay. And then in this point, when the force is applied, this node will also displace, will also move in one-dimensional manner. That displacement, we call it UI. U is displacement around the x direction. Usually we use U for the displacement around the x direction. In the y direction, displacement is V. Z direction is W, UVW. Okay. So here, once you see the UI, that means is the displacement of node I is a subscript around the x direction. You will immediately know this. And then, you know, here there are no E, right? No E as the superscript. Why? Why there's no E here? The reason is because this node, this displacement is shared by multiple nodes. You will have like here, one node. When this one moves, it has a displacement. That displacement is the same for this point of the spring, for this point of the spring, and for this point of the spring, for 1, 2, 3, respectively, right? But the force is not shared. Force here, you have a force around the spring 1. You have a force around spring 2. You have a force around spring 3. They added together will be in equilibrium with the external applied force F2. Okay, force is not shared. Displacement is shared. Do you follow me? Do you guys follow me? Yeah. Okay. Okay. Very good. Very good. So that's how we denote the important information for the node I. We apply the same thing to the node J. So you have the UJ, FJE, right? So that's the force on the J, node J. Okay, and that belongs to the element E or spring E, right? So here, as I said, the force applied to a node is these two. Displacement on the node is UI, UJ. Now, once we know UI, UJ, right now we assume all the displacement are from the left to the right. We assume that. Now, once we know that, we will be able to find out the net length change of this spring. That is actually the UJ minus UI, okay? Because this is the x direction. UJ minus UI gives the net change of the displacement. So here, delta E, delta means net change, or call it elongation. Delta E, elongation means is increased, but it can also decrease if it's shrink, right? When the spring is under compression, it's shrink, or it can be no change, right? Here, elongation means there's net change of the spring. So use delta E, that is UJ minus UI. If UJ is larger than UI, means that this spring is elongated. If UJ and UI equal, means this spring is not changing their length. If UJ equal to 0 and UI equal to 0, that means there are no movement at all. If UJ and UI equal and also has non-zero value, means this whole spring is have a rigid body motion towards the right-hand side. They're moving, but they have no net change. Okay, so that's the elongation definition. Once we know the elongation, we can find out the force on the spring. That is basically using the Hooke's law. You multiply elongation with the spring constant linearly, and then you get the force in the spring. This force we usually write P, capital P, and with the E, P E. Okay, this is called the net force in the spring E, Yeah. So Tara has a question. Memorize all those formula. Run on the. You will naturally memorize this when you repeat, do the problem again and again. Okay, you don't need to keep memorizing them now, but when you practice homework problem examples we give, you will naturally remember it, because this notation actually are very easy to memorize. to be memorized. Okay, very, very intuitive. So don't worry at all. No pressure at all. Just follow me to use them now. When you use them again, they are in your brain. Okay, they will be in your brain. Yeah, very good, very good. So with this force, we will once we know this force, we will know this force actually equals to Fj. Okay, actually equal to the Fj. So here Fj force, they are actually when this spring is under tension, under some external force, they will generate internal force, but the whole spring is held in a static way. They are not in an accelerated manner, right? They are no accelerated manner. Then that means if you add internal force and external force together, then they equal to 0, because F equal to ma, right? So there are no no acceleration. There are no net force applied. In this spring, actually, external force and internal force, they equal to each other. In that case, Fj equals to P. Fj equal to P, and Fi will be in balance with Fj. That means Fi plus Fj equal to 0. Fi is actually the inverse of the Fj. Okay, so this means when this spring is under Fj force on the node J, it also under another reaction force on the node I, which has the same magnitude, but in the opposite direction. These two forces applied to this element, resulting in internal deformation of the spring and the internal generated force based on Hooke's law. But that internal force are in a balance with the external one. And once the balance, we only need to consider the force on the node. We only consider these two, and these two added together is in the equilibrium. Okay, so that's the overall concepts you need to understand. Whole spring is deformed by external force, but the whole spring is in the force equilibrium. And the denotion is we have the force on the node written as small f, and I is the node number, E is the element number. So these two are most important. Okay. Now, once we know this, we rejoin the element here. Once we know this, we can start to write the equation based on the Hooke's law. So we can write on the node I point, we have Fi equals to spring constant times Ui minus Uj, because we stand on the point of I. So we look at the Ui minus Uj. Use J as a reference. So Ui minus Uj, that is the displacement of node I with respect to the J. That will give us the force that applied on the node I. We can also stand on the point of J, node J. Then we write Fj equals to spring constant times Uj minus Ui. Uj minus Ui. I write it here minus Ui plus Uj is the same thing. I write it in Ui first is for the purpose I will explain very soon. Okay. So, but this is the same thing. This means force applied to the node J equal to spring constant times the deformation of the spring. Okay. So then we rearrange it, make the Ui first minus Ui plus Uj. Once we arrange it this way, remember in the mathematics class we discussed about this. If we have a set of equations, we can rearrange them into the multiplication of matrix and vectors, right? So in this format, we can actually extract the k out into this format, and extract the uj out into a vector, right? And then extract the f out into a vector. Now it shows on the right hand side that k times ui minus K times Uj equals to Fi. That exactly, if you extract the K out, that exactly is this equation, right? This equation. The second row of the matrix times the vector again equal to the force. That gives the first this equation, right? You can rearrange it, and give this equation, right? Do you guys follow me? Okay, another question. Are there always two nodes? Are there always two nodes in per element? Mac asked this excellent question. Those are excellent questions. Good. They are not necessary. The answer is not necessary. For this element we are talking about is a 1D element in one dimension. In one dimension, you only have a left and right. You don't have other degree of freedom. If we have a triangle element, then you will have 3 nodes. If you have a square, then you have 4 nodes. Okay, so we will, but to solve those more complicated element questions, you will use the same way as I described here. Use the same principle. Here, once you master this 1D problem, you will be able to solve 2D, 3D problem in a very easy way. Sometimes the element has 8 nodes or 10 nodes. That's also possible for very complicated question. But you use they are corresponding governing equation can all coming from those fundamentals. Okay, Mark, very good question. Very good question. Now, this format can also be written, can also be abbreviated into this form, right? We can write a K like a matrix now, not K. This spring constant we write it into the bold shape now, bold shape, right? That means this is a matrix now, right? It's a matrix. Now, this matrix times the vector, displacement vector equal to the force vector. And then displacement vector can be written into a vector Q, vector form, Q form, right? Bold. Force vector can be written as bold F form, right? Fe. Now, this means element E, for the element E, so this element E, when it's in the equilibrium, its displacement and its own stiffness and force form this kind of relationship. Okay, from this relationship. This relationship can also be written even more simplified as K dot product Q equal to F. K is the matrix. Okay, K is matrix. Here, remember previously we said the convention is the capital bold symbols, right? Here we don't write it in the capital because the reason is because this is for a single element. In our system, we have many these elements, right? In the previous one, we showed we have many spring, right? Many spring. They actually, each one you can write this equation. Each one you can write this, and then totally together you assemble them together into the global form for that whole system. Then you make the whole system into a capital matrix symbol. Okay, so they have the spatial name. This K is called a stiffness matrix. Stiffness matrix of a single element. Stiffness matrix of single element. For the single 1D element, you have only 2 nodes. Then that matrix, that means it's only 2 by 2 matrix. Okay. Q is the vector of displacement. It's also called the vectors of degree of freedom. And then F is the vector of element force. That is the force applied to the 2 nodes at the extreme point. Okay. Now, this stiffness matrix has some very spatial properties. It is a square matrix, and because it relates to the same number of the force as the same number of the displacement, because they are all applied to the same node. This stiffness matrix is symmetric. Okay. It is also singular, determinant equal to 0. So this cannot be inverted. Okay. For the single element, they cannot be inverted, singular. It is also positive semi-definite. Okay. So this is important properties of stiffness matrix. Today we can stop here. It's 1:40 now, and we will continue to discuss about this, and then we will assemble them together into a bigger global matrix. Okay, that's an exciting material. Okay, good. Yeah, thank you guys. Excellent.